Have you ever wondered how a machine makes a decision? Not a complex one, but a simple, fundamental yes or no choice that could have huge consequences? Well, today we're going to pull back the curtain and build a tiny digital doctor to see exactly how AI learns to make these critical calls.
So, here's the big question for today. We have one single piece of information, a patient's blood glucose reading. That's it. From just that one number, can we teach a machine to reliably predict if that person has diabetes? The stakes, as you can imagine, are incredibly high.
The tool we're going to use for this job is a real workhorse in machine learning. It's called binary classification. And honestly, the concept is pretty simple. It's all about taking data and sorting it into one of two buckets. For us, those buckets are diabetic or not diabetic. A clear, straightforward binary choice.
Okay, so where do we start? Well, just like any medical student, our digital doctor has to hit the books. It needs to study past cases, to look at real data, and to start learning the patterns that separate one diagnosis from another. This is the training phase.
And this table? This is the model's textbook. It's super simple. On the left, you've got the blood glucose level, we'll call that X, and on the right, you have the actual known diagnosis, Y, where 1 means yes, diabetic, and 0 means no, not diabetic. The machine's entire job is to figure out the hidden connection between these two columns. Now, it's really important to be clear about what we're doing here and what we're not doing. We're not doing regression. That would be like trying to predict a patient's exact blood sugar value tomorrow. No, we're doing classification. We don't really care about the specific number, we just want to know which category, which class it belongs to.
And here's the key, the real magic. The model doesn't just spit out a yes or a no. It's more subtle than that. First, it calculates a probability, a score from 0 to 1. You can think of it as its confidence level. You know, a score of 0.9 means it's pretty darn sure the patient has diabetes. A 0.1 means it's really confident they don't.
So how does it come up with that probability score? Well, it uses a classic algorithm called logistic regression. And what it does is generate this really elegant S-shaped curve. You can see how as the blood glucose level gets higher, the probability of having diabetes smoothly climbs from basically 0 to almost 100%.
But a probability isn't a final diagnosis, right? We need a clear answer. So, we have to draw a line in the sand. We set a decision boundary, a threshold, right at 0.5. If the model's probability score is above that line, we'll call it a yes. If it's below, we'll call it a no. It's that final step that turns a number into an actual choice.
All right, class is over. Our model is trained. Now it's time for the final exam. This is called validation. We're going to show it 6 brand new patients it has never, ever seen before. We know the real answers, but our digital doctor doesn't. Let's see how it does.
So, how did it do? Let's look at the results. We can see the model's predictions right next to the actual diagnosis. And it does pretty well. It gets most of them right, but look at this one. A patient with a blood glucose of 87, who we know has diabetes, was predicted as not diabetic. That's not just a mistake. In the real world, that's a serious error.
And that one error right there proves that just saying it got 5 out of 6 right completely misses the point. We need a much smarter, much more detailed way to grade our model's performance. We need to understand the types of mistakes it's making.
This, my friends, is a confusion matrix, and it is the absolute best tool for this job. Think of it like the model's detailed report card. It breaks down every single prediction into 4 simple categories. True positives and true negatives are the ones we got right. Awesome. False positives and false negatives, well, that's where we went wrong. And you can see our one big mistake sitting right there. 1 false negative.
So, let's start with the metric everyone knows, accuracy. It's super simple. It just asks what percentage of the time was the model correct. You just add up all the correct guesses, the true positives and true negatives, and divide by the total number of patients.
For our model, the accuracy is 0.83, or 83%, which sounds pretty good, right? Like a solid B on a test. But here's the question you have to ask. If that other 17% it got wrong is a person who needs medical treatment and doesn't get it, is 83% really good enough? This is why accuracy on its own can be really misleading.
And that brings us to a metric that, for our case, is way more important. It's called recall. And the question recall asks is simple but powerful. Of all the people who were truly sick, how many did our model actually find? This metric is all about not letting anyone slip through the cracks. It's about minimizing those dangerous false negatives.
Our model's recall score is 0.75.
So what does that actually mean? It means that of the 4 patients in our test group who really did have diabetes, our model only caught 3 of them. It missed 25%. In a real medical screening test, that is a failing grade, no question. Now, on the flip side of that coin, we have precision. Precision asks a different question. When our model does raise a red flag and says, hey, I think this person has diabetes, how often is it right? This is all about trust. We don't want to be crying wolf and sending healthy people for a bunch of stressful, unnecessary follow-up tests.
In here, our model gets a perfect score, 1.0. That means, at least in this little test, every single person it flagged as diabetic actually was diabetic. It never raised a false alarm, so it's incredibly trustworthy when it speaks up. But as we saw with recall, it's also maybe a little too cautious, a little too quiet.
See, there's this natural tension between wanting to catch everyone, high recall, and wanting to be right every time you make a positive prediction, high precision. So how do you get one number that respects both? Well, that's where the F1 score comes in. It's a clever way to find a balance between the two.
Our F1 score is 0.86, and this number gives us a much more nuanced, a much more balanced view of how our model is doing than accuracy alone ever could. It tells us that, all things considered, the model is doing a pretty solid job, but there's definitely room for improvement.
But wait a second. All of this was based on our decision to set the threshold at 0.5. What if that was the problem? To really truly understand our model's potential, we need to see how it would perform across every possible threshold we could have chosen.
And this graph, the ROC curve, gives us that big picture view. On one axis, it shows how good the model is at catching sick patients, that's the true positive rate. On the other, it shows how often it accidentally flags healthy patients, the false positive rate. A perfect model would have a curve that shoots straight up and to the left. The closer our curve gets to that corner, the better our model is, fundamentally.
Now we can summarize this entire beautiful curve with just a single number, the area under the curve, or AUC. Our model gets an AUC of 0.875. And since a perfect score is 1.0 and a score of 0.5 is no better than just flipping a coin, a score of 0.875 tells us that our simple model, built on just one piece of data, actually has some pretty strong predictive power.
And all of this brings us to the final, crucial question that no machine, no algorithm can ever answer for us. For a medical test like this, what's actually worse? Is it missing someone who's sick, a false negative? Or is it mistakenly worrying someone who's healthy, a false positive? The answer to that question determines which of these metrics we should care about most, and that is a choice with very, very human consequences.